So this is the Mathcad for the concrete cantilever retaining wall, and this is straight out of the Module 6 of the earthquake resistant retaining wall design. So, modes of failure, as we've discussed before, you can look at wall stem failure, foundation bearing failure, sliding failure of the wall, so that's the foundations moving. The fourth mode of failure we won't look at today, but they should be considered by your geotechnical engineer. So here are the diagrams for those modes of failure. So your base of your stem is failing, you've got too much moment in the base of your concrete wall for the concrete capacity to carry it. The next two are about geotechnics, so the ground underneath can't take any more load and basically moves and yields under the pressure. Alternatively, they can slide out of the way, so you're pushing on the back of a wall, it just might move out of the way. And finally, your deep-seated rotational failure, you have a guess at which of the circles that will cause the failure, so you're looking at the lower limit for that. As I keep reminding you, these are just some of the models that can be used to analyze your retaining wall. And remember, all models are wrong, just some of them are useful. And that's probably doubly so for geotechnics and even more so in New Zealand. So we put in our wall properties, so the length of the base, width of the stem, and so on, how long the toe is and the heel is. That's just straight out of the example, and derive the width of the footing and the weight of the footing from the parameters given above. We assume from soil parameters that our unit weight of soil, gamma S, is 18, our angle of shearing resistance is 30, and our inclination is 0, of course. And we've got a cohesion, effective cohesion for the drained condition of 0. And from that very old graph, that's the nav effect graph that's provided in the example, you take the coefficient of active earth pressure, KAH, as 0.3, and the coefficient of passive earth pressure as 5.5. The 5.5 derives from the figure 0.65 multiplied by the 0.85. That's the fiddle factor you'll find in the table next to the graph. Yes, very complicated. And for the earthquake case, we're looking at undrained short term, and we take our angle of shearing resistance as 0 and our cohesion CU as 50 kPa. Our imposed loading on the surface, W, in this case we've called it Q, that's 5, but in cases where it's stabilizing, we've put a smaller factor in there. Now looking on to the seismic parameters. Now this example is based in Christchurch, and most of the examples based in that MBIE guidance are taken from Christchurch. So it's assumed it's Class C soils, and you're looking at a 500-year return period. So from the example, we've given that the A max is a 0.4 of the G, acceleration due to gravity. Topographic amplification is 1, so we're not near a cliff edge or a ridge top. Our wall displacement factor is 0.5 because of the scenario we're looking at. So that equates to a horizontal acceleration of 0.2 G. Now we're ignoring the vertical acceleration for simplicity. There are nearly always vertical components to your earthquake action, but for most of our designs, we tend to ignore them because they're usually quite small. So because we've adopted a WD of 0.5, we're assuming that the wall and the retained ground are likely to yield. And that because of that, you're going to get permanent displacement behind the wall during the design earthquake event. The wall must be sufficiently robust or ductile to accommodate that movement, and some settlement is expected following the earthquake. So that's the model we're using. to work out what the loading is on our cantilever retaining wall. And we'll keep this to the side, so it's a reminder of what's going on. Gravity case will usually be the dominant load case, not always, depending on where you are, but we do need to check against the seismic load case. For the simplified procedure, we look at the middle third rule, and it's much easier if you do apply the middle third rule. Otherwise, it's a very complicated analysis. And we've got to take into account the applied horizontal loads and the soil pressures. So here are our strength reduction factors that we'll be looking at, or resistance factors. So when we're looking at bearing in the gravity case, we've taken this from the NZBC VM4, and we're looking at a load resistance or a resistance factor of 0.5. And against sliding, we can use 0.8. And for passive pressures, we can use 0.5. Where we're stabilizing, we apply a 0.9 factor. Where it's destabilizing, we apply a 1.2 factor. Okay, so first we need to check the middle third rule. And we do this by taking moments about the toe. That's that point there. And so we work out what the active thrust is. So our PA, there's our PA, and it's worked out as the coefficient of active earth pressure multiplied by the soil unit weight multiplied by the height of the retained soil squared. And we take that as half of it because it's a triangular distribution. There is, of course, a vertical and a horizontal component to these because the passive active earth pressure is acting at an angle. So our active soil thrust, the horizontal component is 20 kilonewtons per meter, while the vertical one is 11. So that's for the soil. Let's look at the result of the surcharge. The surcharge is on the top of the retaining wall, and again that effectively is at an angle. So we have a vertical component because of that angle of 2.2 and a horizontal component of 3.8. We can also allow for a surcharge above the heel. That's this thing here marked as W on the diagram, but it's worked out as PQ here, of 3 kilonewtons per meter. Then we work out the moment from the horizontal active pressure, and that by taking the forces and multiplying by the lever arms, and we get out 31 kilonewtons. The moment from the vertical active pressures, the vertical components, which potentially can be restoring, works out as 25 kilonewtons. That really should be kilonewton meters per meter. And the moment from the surcharge soil above the heel, and again that's restoring, is 4.05. So the full restoring moment from the self-weight of the soil, from the self-weight of the wall, and works out, if you multiply the weights by the lever arms by the stabilizing factor, in this case 0.9, we work out as a restoring moment of 74 kilonewton meters per meter. The net moment about the toe, that's neglecting this passive pressure, works out as 72.9 kilonewton meters per meter. So your factored vertical loading on the footing works out again. You multiply the weights by a stabilizing factor and add it up with your passive resistance, active pressure, and you get your 79 kilonewtons per meter. So what we do is we work out where it is applied. So we take our moment and divide it by the vertical component as basically the resultant, and we find out where the middle third is. So it's somewhere between L/3 and 2/3 of L. So our applied position, so the line of action is in the middle third because it lies between 1/3 L and 2/3 L. That's okay. If it doesn't, I suggest you adjust the dimensions of the wall to suit. So then we look at the bearing capacity in the long term, so the drained bearing capacity. So our effective footing width we've worked out from above. We've also got our ultimate vertical load from above as well, and our ultimate horizontal load, again, we've worked out from above. As we've said, the ground slope in front of the footing is 0 and the tilt of the footing is 0. Our soil cohesion is 0 and our effective angle of shearing resistance is 30. We're taking the adhesion under the footing, we're multiplying it by 1. There are different factors you can use there, but in this case we're multiplying it by 1. So here are the bearing capacity factors, and again they're given in B1 VM4. Now you can use the graphs given in there, or you can use the formula given in there, but if you use the formula, spot the errors. These numbers, these equations given in the B1 VM4 are not quite right. So in our case, the bearing capacity factors NQ, NC, and N gamma work out as 18.4, 30.1, and 22.4. B1 VM4 also provides figures for our shape factors and our depth factors. Those work out as slightly above 1. And the load inclination factors are also given in B1 VM4, and they work out as the 0.3, 0.1, and 0.278. Because our ground is flat, our base is flat and horizontal, our ground inclination factors come out as all 1. Now, when you multiply all those figures above, you get the ultimate bearing strength given by the formula, again taken from B1 VM4. So our design bearing capacity is 78.3, and in our case our factor of safety against bearing works out as VU star over the VU. So our bearing capacity is actually smaller than the applied load. So sorry, the applied load is bigger than our capacity. And to change that, we can alter the width of the footing to increase the area for the bearing capacity. However, what I've done there is use the parameters given in B1 VM4. I've also got another calculation, which is taking it straight from the Module 6 of MB, and they use slightly different parameters. They use parameters for the load inclination factors given here, and I think that's come from a formula by Vesek. And the load inclination factors end up slightly larger, so your bearing capacity is also slightly larger. So your design bearing capacity works out as 84.1 kilonewtons per meter, which gives our factor of safety in bearing as slightly over 1. How convenient. So we move on to the wall sliding. That's our third case we're considering today. And for wall sliding, we factor down the self-weight components because they're stabilizing and apply a factor of 0.9. The vertical component of active thrust is not factored, it's just 1 as before. And the vertical component of the passive resistance is also not factored because in fact it's destabilizing in this context. So let's check the wall sliding on the base of the footing. So we work out what the weight of soil trapped under the footing is. We've taken our interface friction angle for passive pressure as 20 degrees. We've got our passive resistance PP, that's that thing down here. That's 10. There's a horizontal and vertical component of that because it's at an angle. So our horizontal component is 9.4 and our vertical is 3.4. We can work out what the friction under the footing is as 47. and the factored ultimate resistance as 42. So our factor of safety works out as a 1.16, so the applied load is slightly smaller than the capacity. So the wall bending strength, this is again in the gravity case, so the wall might fail in bending down here, when the moment is at the maximum at the base of the cantilever wall. So you work out what the bending moment is in the stem. Now, for some reason, the example has moved on to a different way of working out what the active pressure is, and it's using the MO equations. So the coefficient of active earth pressure applied to the back of the wall is that large formula we've given before. And from that, you can work out what the active thrust of the soil is. And the horizontal component you need to know because we're looking at the wall, not the base. And then we take the horizontal component of the active thrust due to the surcharge load. And then we calculate the ultimate bending moment in the stem. You take the horizontal forces and multiply it by the lever arms, and you get a 31.25 kilonewton meters per meter. And we'll go on then separately to calculate the capacity of the wall itself in terms of the concrete section capacity. That's in the next example. For now, we'll go on with the foundation bearing because we're still sticking with the MBIE example. So we need to check it in the earthquake case. And so we use a different formula. And we use our cohesion as the SU value, our undrained shear strength. And we're taking a KP, a passive coefficient of earth resistance, of 1, which is rather conservative, but it's safe. Again, we check the middle third rule, and then when our surcharge is actually stabilizing, we're using a 3 kPa. For the factored surcharge case, where it's destabilizing, we're taking an earthquake load case in this case, so we've got a reduced live load for our surcharge. So again, our seismic coefficient is 0.2. Now our resistance factors are all scaled down to 1 because it's an earthquake case. From the Mononobe, Okabe, and Capilla's earth pressure coefficients, we can calculate that the active earth pressure coefficient, KAE, is the 0.471, as we've seen before from this very large equation. And that's popping in this value theta. And you get the theta to take into account the acceleration due to gravity of the earthquake load. From that, you can calculate the active thrust due to the soil, the active thrust due to the surcharge, and then the surcharge above the heel, which is potentially restoring. What we need to do then, because it's the dynamic load, we need to work out what the inertia is of these wall structural elements located behind the heel. So the lump of earth behind the heel is treated as part of the wall, and they're added as follows. So the inertia from the foot works out 2.2, and then from the key and the stem and the soil and so on. From that, you have the moment from the horizontal components. As you take your horizontal values and multiply by the lever arms, and you get out 31.179 kilonewton meters per meter. The moment from the vertical components works out as 39, and the moments from the surcharge above the heel works out as 4.05 kilonewton meters. So the total moment from inertial forces works out as 17.4. So the restoring moment from the self-weight of the wall and the soil above the heel is calculated again by taking the weights and multiplying by the lever arms. You need to look at this diagram on the left to work it out, and that pops out as 82.5 kilonewton meters per meter. You do the summation and you work out the net moment. And so the resultant force has an arm somewhere between 1/3 and 2/3 of the width. So we're in the middle third. If we're not in the middle third, you need to move the dimensions. The next thing to look at in the earthquake case is the bearing capacity. So this is again short-term and undrained. So we've gone through the soil parameters before. We've worked out the loading before, vertical and horizontal. And we're using again adhesion under that footing of 1 CU, which works out as 50 kPa. And we work out our bearing capacity factors again. Now, bear in mind that bearing capacity factors differ depending on when you're looking at undrained or drained situations. So B1 VM4 gives you an NC value of 5.14. And then you can easily derive the NQ and N gamma either by looking at the graphs or by popping them into the equations given in B1 VM4. Similarly with the shape factors and the depth factors that we've seen before. The load inclination factors are different this time because you've got slightly different loads. The load inclination factors remain as 1, and so we get an ultimate bearing strength in this case of 232 kPa. And so our factor of safety against bearing failure is over 4. So we can see that our seismic load case is not the governing case. Now look at wall sliding in the earthquake case. So we're taking our coefficient of passive earth pressure as 1, which is again quite conservative, but it's at least safe. We work out what our passive resistance is, and it's 21 in this case. And our sliding resistance works out as 104 kilonewtons per meter. So our factor of safety in sliding is over 2. So we're happy. And again, earthquake case is not the dominant case. So looking at the wall stem bending strength, so this is again the bottom of the wall, and it's about the structural failure of the wall. And you're looking at the earthquake case. So we take the interface friction as 0. We work out the coefficient of active earth pressure that we worked out before, bring that down. Active thrust from the soil is 26.5. Active thrust from the surcharge is 4.7. And the ultimate bending moment in the stem works out as 31 kilonewton meters per meter. And that you can then use to design the concrete wall.